Before I start, anybody have any questions? Yes.
When you analyze a structure, do you pick an origin for the whole thing or for every?
Yeah, so that's a good question. The way to think about it is you don't change the origin, but you kind of. Okay, so let me do.
So it's there. It's just off the actual.
You just don't really use it for the calculation. So let me just try to clarify that. So do you choose a new origin for every body in a structure? And I think the best answer is not really. But practically speaking, you can think of it that way. And, okay, the reason that you can think of it that way is that if you look back the first time I talked about that row vector, there are two ways you can calculate the row vector. The first one is calculate the coordinates of where the force is applied, calculate the coordinates of the about point, and subtract. Okay, so that's the first way. But the second way, this is the important one for what we're talking about here, is think of putting your origin at the about point. Then the row vector is the coordinates where the force is applied. So you're not really moving the origin. It's just a calculation, I don't know, calculation thing. It's a calculation thing. Okay, so for example, I'm not going to go through this whole problem, but let's say, let me do a really easy one with really easy geometry. So let's say we have two members. They're each 1 meter long. And let's say there's a downward force of 500 newtons and a horizontal force of 1,000 newtons. And let's say that the real origin is here. And I'll number it 1, 2, like that. So a free body diagram of member 1, and I'll try to point out where the thing that we're talking about, where that comes up. Okay, so a free body diagram of member 1. And these are supposed to each be a meter long. I didn't write that. So what are the forces acting? There's a 1,000 here. Here there's a force on 1 by 2. And here there's I'll call that RA. Okay, so how do we calculate that row vector? Well, if you want to use the real coordinate system, if you want to use the real origin, you can calculate the coordinates of P, calculate the coordinates of what you want as an about point, and then subtract those points. Or you can also just say, so let's say that this is what we choose as the about point, okay? As a calculation thing, we're not actually moving the origin, but as a calculation thing, we can say, let's act like our origin is here, and then just calculate the coordinates of the other points. So let me letter these. I'll call that A, B, C. So the row vector for B then is 0, 0. And the row vector for A is 0, negative 1. Okay, so really we didn't move the origin, but if you thought of it as moving the origin, it wouldn't cause any problems with your calculation. And then if we go to a free body diagram of member 2, we have the 500 Newton force down. We have the negative force on 1 by 2. And we have the reaction at C. Let's say that this is our about point. So the row vector at B is negative 1, 0. The row vector at C is 0, 0. I left off the row vector of the 1,000 here, but I'll call it row 1,000 for the member above. That would be 0, negative 0.5. For this one, the row vector for the 500 would be negative 0.50.
Just out of curiosity, why does that work? Is it just because the forces are proportionally the same, or?
Well, it's just because that row vector is a difference between points. And so if you make the thing you're subtracting 0, then the difference is just the other one, you know, like...
I mean, why do the calculations for rotational Newton second law end up with the same results?
Yeah, because the definition of the row vector is this, you know, and so if you make your A vector 0, then the row vector is equal to that P vector. It's a difference. It's a displacement, you know.
Okay.
And so displacements don't care about what you call the origin. They only care about the orientations of the axes.
Okay.
Yep.
So you can change the about point because it's in static equilibrium. Yet if it was dynamic, could you do it as long as it was...
No, you can still do it in
or
dynamics.
the center of mass?
you can still use this same approach with dynamics.
Okay.
It just has to do with the fact that this is a displacement between 2 points. It's a difference of 2 points, and so it's the same thing as, remember, like conservation of energy. If you calculate you always get to choose what you're going to call your zero height. Remember that, if you're using gravitational potential energy?
Yeah.
Okay, so that changes what the potential energy is at a point. You know what I mean? But it doesn't change what's important, the difference in potential energy, because you're subtracting out. Here. This is better. Let's think of two different origins. So there's one. Whoops. There's the other one. Okay. And let's say this is the point P, and this is the point A. Okay. In the green coordinate system, you can represent, okay, well, in the blue coordinate system, these are, let's say it's like this. There's the vector for A. There's the vector for P. In the green coordinate system, to represent A and P, because of the way vector addition works, you can represent these as a vector going to the blue origin plus a vector from the blue origin to the point. And here you can represent A as a vector from the green to the blue plus that. And so what you get is this is clearer in my head than it is in what I'm saying. That I'm 100% sure of. So rho in the green coordinate system is equal to, so let's call this vector D. Okay, that's a vector going from the green to the blue. And so rho in the green coordinate system is P in the green minus A in the green, which we can re-express as P in the blue plus D minus A in the blue plus D. The D's cancel, and you get P blue minus A blue, which is rho blue. You end up canceling out the vector that goes from one origin to the other origin. And so no matter where that origin is, your row vectors are the same. So I think maybe we should, unless you have any specific questions, I think we should stop there. If you want to figure it out, you can figure it out from this. If you don't want to figure it out, you're just like, if you stopped listening the instant I said, yeah, you can think of it as moving the origin, that's fine with me too.
So
Yep.
the only rule is that for each body, it has to have the same origin and about point.
Inside the same body, keep the origin and about point the same.
But in structures, you can use different about points or origins.
Every rigid body can have a different about point, and practically speaking, different origin, although really, technically, that's not what you're doing.
And it's because of math.
It's because of math.
That's what I was-
Okay, yeah. Okay, so the next thing I want to talk about is, this isn't something that you have to use, but if you're curious about it, sometimes it can save you some variables and stuff. The two-force member simplification. And this is what the truss simplification is based on. So remember, if a body has only two forces acting on it, and let's say two force vectors acting, and no other loads of any kind, so there can't be couples in addition to this or anything. And the body is in static equilibrium. That's always in this class. But not in dynamics. Then those force vectors are equal and opposite. And act parallel to a line between the two force locations. So here are two examples. Most often you have straight members because when you're trying to use members to sustain big loads, straight members do it better. So in this case, if you have forces at the two ends, the only possibilities are this, pure tension, or this, pure compression. Okay, so now what if you have a member like this, and the forces are here? Well, draw a line between those two forces, and all this member can do is this, or this. It has to be in static equilibrium for this to be true, because obviously there's nothing that says you couldn't kick one side of this harder than the force is applied there and it'll accelerate off, you know. But if these are going to be in static equilibrium, that has to be the case. So, with any two-force member in statics, you can replace the member with a super cable. I just made that word up now, super cable. And here's what a super cable does. So a regular cable, you know the direction of the force. You know it's pulling on the member. You know you have to have a positive value for your tension. A super cable can have a positive or negative tension. So it can apply compression. It can push on the member or pull on the member. So it can push or pull. Meaning tension is positive or negative. Regular cables, no, only positive. Okay, so let's see how this works. Well, let's do that same simple geometry that I just did. I'm going to have to change this problem a little bit. So this height is 1 meter. This width is 1 meter. And let's say we have, let's apply both of these forces at the pin. We'll say there's a downward force of 1,000, a horizontal force of 2,000. I imagine that your phone, like you getting a text and being like, oh, the Civil War started, everybody. I'm just waiting for that to happen. Like Wednesday, we're all going to come to, like, we'll come to class like normal, but we'll all be wearing like ragged clothes and like war paint and like covered in pig blood and all. I'll edit that out of the video. Okay, so in this example, why couldn't I just use the example I made before? Yeah, exactly. There's 3 forces. There's forces at the pins, and there's forces in the middle, so we can't use this simplification in this case. Yes?
Just out of curiosity, what's the practical application of this if you can't have a force such as weight involved?
Because a lot of times the weight is so much smaller than the other applied loads that you get just your answers are perfectly good without including the weight. But you're very right that that is a major weakness of this method. Major. Because weight is one thing that things with mass have consistently. Okay, so what are the external loads? I'm not really going to edit that out of the video. That was also a joke. That would take way too much work. Okay, so using the full approach, how many variables, how many equations would we have here? There's an easy way to do that calculation. Think of the number of equations. 6, because we have 2 members. Each one gives us Newton's second law and the rotational equation. So 3 plus 3. So we'd have a system of 6 variables, 6 equations. Okay? So now let's do this approach using the super cables thing. Trademark. Well, this is sort of a funny problem because if we treat these as cables, like what are they applying forces to? In this problem, all they're applying forces to is the pins. So I'm going to do a free body diagram of, let me still label these. So I'll call that A, B, C. I'll call this member 1 and member 2. And I'm going to do a free body diagram of the pin at B. So there's the pin. What forces are acting? Well, there's a tension in this cable 1. It's really a member. I'll call that T1. And there's a tension in this cable 2, T2. And then there's these 2 forces, a downward force of 1,000 newtons and a horizontal force of 2,000 newtons. Any questions about that? Newton's second law says positive 2,000, I'm lumping these two together, positive 2,000, negative 1,000, plus T2, 0, plus 0, negative T1 is equal to zeros. Yeah, we're going to treat it like it's tension, but they can come out negative. 1 is going to come out negative, I hope. And so there's no this doesn't have any size, the pin. So we're not going to have rotational Newton's second law. So we have 2 equations. How many variables do we have? 2. And we can solve this already. This is sort of an extreme case of the benefit of this approach. The first one says, well, they're both in compression. T1 is equal to negative 1,000. T2 is equal to negative 2,000. Negative means compression. Nope. We put these in as those. I think the easiest way to think about this is in terms of Newton's third law. If member 1 is applying a downward force to that pin, then that pin is applying an upward force to the top of member 1. And so a positive value of T1 would mean that that member 1 is in tension.
Okay.
And yeah, same with member 2. So we're assuming it's in tension. If we get negative values, it's in compression. And so the external loads are just this simple. Member 1, nope, I drew it in tension. It's in compression, so member 1 has a force like that and a force like that. And member 2 has a force like that and a force like that. So that was pretty simple. The the problem with this, well, I mean, I've gone through the issues before, but you have to be really careful about identifying two force members, because this approach will make, like, you can use this approach in the wrong setting, and nothing about using it will tell you that it's going wrong. It'll give you an answer. That answer just doesn't mean anything. Yep.
So that's only if there's two external forces, because we have our reaction forces, and those aren't a part of the members.
So any forces, there can be a whole bunch of different things causing forces, but as long as they're causing those forces at the same point, they just add up to a single force vector.
Okay.
So the key is that each of these two members has forces acting at only 2 points. Okay, so that's the key thing. All right, so let's see how this works in a more complicated structure where not everything is a two-force member. This simplification, you can use it for two-force members in structures that don't include only two-force members. So here's the example. So let's say there's a cantilever beam coming out from the wall. And at the midpoint, there is a member like that. And these two connect with a roller. And then there's another beam connecting the vertical piece to the end of the horizontal piece. Those are pin joints. And then at the midpoint, there's another member connecting to the end. And now there's an external force of 5,000 newtons, making an angle of 30 degrees below the horizontal. We need some dimensions. Let's call this one meter. This 1 meter. And this 1 meter. What are the external loads on each member? All right, so if we did this using the structures method that we've been using, the full method where you don't have to think at all about categorizing different members, how many equations would you have here? Just count up the members and multiply by 3. So 1, 2, 3, 4, so 12. The full method that requires no thinking, just chugging along, 12 equations, 12 variables. Okay, that's not so horrible, but if we recognize, and let me label these. So let's call this member 1, 2, 3, 4, and the joints A, B, C, D, E. You can simplify this a little. If you recognize that members 2 and 3 are 2 force members. Okay, so we're going to treat those as super cables. So now I'm going to redraw this. We have the vertical member. The horizontal member, sorry, there's the vertical member. They're connected by a roller. And now we have a cable there and a cable there. And the external force of 5,000. Remember, these cables can have positive or negative tension. That's what makes them super. And so now I think maybe we're going to get away with just 6 equations on this. We'll have to go through it and see. But you know, we haven't cut it down all the way to a structure made out of 2 force members, but we have taken advantage of that simplification in 2 spots. All right, so I don't know. I guess I'll call it 1. Is that going to be confusing if I renumber that? Call it 1 and 2. Okay, so let's draw a free body diagram first of member 1. At the wall, we have a reaction force and a couple. So that's a fixed joint. In the middle, at D, that's a roller. So that's a pushing contact acting toward the body that we're isolating. I'll call that RD. And then at the end, we have two tensions. I'll call that T1 and T2. And now let's think about a free body diagram of member 2. We have the applied force of 5,000 newtons. We have the pushing force RD that's now acting up. We have the cable force T1 and the cable force T2. And so we have 6 equations. How many variables do we have? 1, 2, 3, 4, 5, 6. We didn't add any new variables here. So 6 and 6. And you can decide, I guess, for yourself, case by case, whether the extra thinking required was worth solving a system of 6 equations versus a system of 12. If you're doing it by hand and you don't have any other options than doing it by hand with substitution, then the answer is probably yes. But since we're in the 21st century and whatnot, we don't do anything by hand, I'd say, to me, the answer is probably no in every case. I would say that's too much thinking. Just go through the method that works all the time for everything, and that's that. Any questions about that? Okay. So the next topic is internal loads and beams. Should we go through that calculation? Anyone want to see that or no? There's no differences. You treat it like it's cables, except now, let's go through it. Let's be honest. There's not going to be any more classes after today anyways. Yeah, the country is just going to be like a burnt black hole. Yeah, it should be. Okay, I'll tell people. They haven't listened in the past, but I will tell you this much. And I don't mean to be like, I'm not trying to brag or anything, but in the last few weeks, Hillary Clinton has been sending me a lot of emails. Like, I think she really has started to rely on my counsel. And like so many that I can't even reply to them all in a thoughtful way, I have to admit. Like, sometimes I don't reply at all, and
Emojis.
yeah, right. Okay, so let's do this. So body 1. Where should we put the about point? I think probably the easiest place to put it is there, because otherwise the cross products with those known directions, it doesn't really matter, is the answer. Put it wherever you want. So we have to come up with, well, this is the about point, so the row vector for T1. Yeah. I got to recalibrate this screen. Okay, so the row vector for T1 is 0. The force vector, what direction is that pointing? Well, these two lengths are the same, so that's a 45-degree angle. So this force is 0.7071 T1, 0.7071 T1. Take the cross product and you get 0.
Why would you even bother writing that out if you know it's just an equal 0?
Yeah, that's a good question. Yeah, you can leave that off. T2 is also at zeros. You do need to write out the force vector, though, because that is going to come into it. It's just the moment that isn't going to come into it.
Okay.
All right, so T2. What do we know about the angle? So that's at the midpoint, right? So what's the arctangent of 0.5? I think it's like maybe 26.57. Someone tell me if that's right. Little by little, I'm memorizing every number in trigonometry. 26.57 degrees. So what's cosine and sine of 26.57?
Cosine 0.894, sine 0.447.
0.447?
Yep.
And then the next force is that force RD. What's the row vector for RD? If our about point is the red dot?
1, 0.
1, 0, yep. The force vector is downward, so that's 0, negative RD. And that cross product is negative RD. The next one is, let's do RE first. So what's the row vector for RE?
2, 0.
Yep, 2, 0. Bless you. The force vector is REX, REY. And the cross product is 2REY. And then the last one is the couple. We don't care about that. There's no force, and so that just gives us ME. So Newton's second law says 0.7071 T1, 0.7071 T1 plus 0.894 T2, 0.447 T2, plus 0, negative RD, plus REX, REY is equal to zeros. And the moment equation says negative RD plus 2REY plus ME is equal to 0. So I'll write these out. 0.7071 T1 plus 0.894 T2 plus REX is equal to 0. That's the first equation. The second equation says 0.7071 T1 plus 0.447 T2 minus RD plus REY is equal to 0. And the third equation says negative RD plus 2REY plus ME is equal to 0. Any questions about body 1? And now body 2. There's the free body diagram. For the about point, let's choose the top. So for the force vector T1, the row vector is 0. The force vector is negative 0.7071 T1, negative 0.7071 T1. There's no moment. Next is that 5,000 Newton force. That's 5,000 times cosine and sine of negative 30. So that's 4330 negative 2,500. That's still at row vector of 0. So there's no moment. Now what's the row vector for T2? The whole vertical thing is 1 meter, so that's half a meter down. The force vector is negative 0.894 T2, negative 0.447 T2. And so the cross product is negative 0.447 T2. And then the last force is that RD. The row vector is 0, negative 1. Force vector is 0, positive RD. And no moment. Newton's second law says negative 0.7071 T1, negative 0.7071 T1, plus 4330, 2500, plus negative 0.894 T2, negative 0.447 T2. Yep, thanks. Plus 0 RD, zeros. The moment equation just says T2 is equal to 0. I'll just write it like that. So our equation 4 says negative 0.7071 T1 minus 0.894 T2 is equal to negative 4330. Equation 5 says negative 0.7071 T1 minus 0.447 T2 plus RD is equal to positive 2500. And equation 6 says T2 is equal to 0. Let's see. So let's write this all out. It seems sort of tedious, but I think it'll be good to put these back, write these back as external loads on these bodies. Yeah.
And then how does the T relate back to the real world? Because we have them in tension, so
Yeah, so that says that the way I have it drawn, that cable T2 is not is not doing anything, I guess. If
It kind of makes sense because the T1 cable would be taking all the force from body 4.
mhm.
So that body 2 would kind of just be sitting there.
Yeah, I guess it's like the the cable, the tension along member 3 is counteracting the horizontal. Well, yeah, I don't know. I wouldn't have thought it looking at it, but what that says is that member 2 isn't doing anything here. And then the variables, we have T1, T2, RD, REX, REY, and ME, and then this is the constant. Okay, so equation 1 says T1s we have 0.707, T2s we have 0.894, REX we have 1s. So 0.7071 T1, 0.894 T2, and 1 REX, and everything else is zeros. Number 2, T1s we have 0.707, T2s we have 0.447, RDs we have -1, and REY we have 1. So T1 0.7071, T2 0.447, RD we have -1, and REY we have 1. Equation 3 says RDs we have -1, REYs we have 2, and ME we have 1. So RD, what was that, -1? I can't store all this. REY is 2. ME is 1. Everything else is 0. Equation 4, T1s, we have -0.7071. T2s, we have -0.894. The constant, we have -4330. Equation 5, T1s, we have -0.7071. T2s, we have -0.447. RDs, we have 1. Constant, +2500. And then equation 6, T2, we have 1. Everything else is 0. All right, well, let's see what happens. If we entered everything right and the matrix tells us there's no solution to this, it means I drew a structure that is either statically indeterminate or would not be in static equilibrium. So could multiple people punch this in? 6,123.6. Okay?
T2 0.
Okay.
What is next in the matrix?
RD.
6,830 and -4320. Oh, yeah. Sorry. And then 2,500 is the problem.
Okay.
And then 1,834.
Okay. So now what does all that say? It says if you take these numbers and plug them back into the free body diagrams, you have the external loads on these bodies. The easiest two are the two diagonal bodies. We know that the one like this, we have a force of 6123.6. Is that in tension or compression? Tension. We always assume positive is tension. So this is going to be 6123.6 that way and this way. This member doesn't have anything acting on it. The vertical member has the 5,000 Newton force. A force this way of 6123.6. Nothing happening at where that second thing is connected. And then down at the bottom, an upward force of 6830. By the way, since these two are acting at a single location, You can add these to get a single vector. And then the horizontal force, or the horizontal member, we have 6123.6 that way. A downward force of 6830. A force vector on the right of negative 4330, positive 2500. And a couple of 1830. And the next topic that we're going into is calculating the internal loads and beams. So figuring out, getting more information about where we're concerned about these different members breaking. And in order to take that next step of calculating where we're concerned about these breaking, we have to start with the external loads on these members. So we have to go from not just go past just calculating these numerical answers to the matrix and interpret them as external loads on the members like we did here. Yep.
On the single vector, you have at the 61, 23.6, and 5,000.
Yeah.
Question I have for you: the 61, 23, is that a negative just because of the x value is going there? So would that be?
Well, yeah. So you would have to you'd have to multiply that by a unit vector to get the components.
Okay. So
And that unit vector would have a negative x and a negative y component.
okay. So now
But this is the way that you write that, because this is saying the direction is that way. That's the unit vector, and you're multiplying it by a positive number.
right. So overall, then, should you have a kind of an offsetting value between the two? Then I'm thinking the
Between those two, yeah.
0.6 minus the 5,000.
Yeah, so it would be like this. Here's how you would do it. You'd have, so this vector would be 6123.6 times its unit vector. I'm not giving myself enough space. Yeah. So this would be 6123.6 times the unit vector for that force, which is negative 0.7071, negative 0.7071, plus the other force expressed as a vector, which was 4330, negative 2500. Can someone tell me what that vector is if you add those two?
Okay, I got it.
Well, it's going to be 0x. And then it's going to be like 1830y or something. Negative 1830y. That's my guess. 6830. Oh, okay. Yeah, that's what I was thinking of.
All right, thank you.
So you have to take those scalar values, multiply them by unit vectors to get the vectors, and then add the vectors. Okay.
Thank you, guys.
Sure. Any other questions about that? Okay, so next time we'll do internal loads in beams. why are we doing all this stuff? I mean, really, like all the analysis we do in this class is trying to get at the question, are we worried that this thing is going to break, you know, or what can we do to make it so it doesn't break? Well, we figured out the external loads. We know how to calculate the external loads in a structure usually. But that actually doesn't tell you, so you might think like, well, I'm going to look for where the external loads are the biggest, and then that's where I'm most concerned about this thing breaking. But it turns out that's not the case. Sometimes it is, but often things are most at risk of breaking away from where the external loads are applied. That seems sort of odd, but often that's the case. And so the next step we have to take is to figure out not just what external loads are applied to a beam, but to figure out what the loads are that are happening inside the beam as a response to those external loads. That's the next step towards figuring out when something's going to break, and that's what we're going to start next time.